Humans are always pushing boundaries, right? Trying to build um, infinitely powerful computers, maybe even true AGI. But what happens when that ambition slams into like a fundamental physical wall? Today we're diving deep into something pretty wild, the connection between black holes and the absolute limits of computation.
It's a fascinating area because it turns out the physics of these, well, incredibly extreme objects, black holes, they actually set the rules for everything else. We're talking the ultimate limits on how much information you can store and just how fast you can possibly process it.
Okay, so they don't just exist within the laws of physics, they sort of define them for information.
Exactly. They embody those limits.
All right, let's break that down. Memory first. Is there really a hard cap on how much data you can cram into a space?
Oh, absolutely. It's called the Bekenstein bound. Basically, any surface area anywhere in the universe has a maximum information capacity. And if you try to push past that limit, try to make information denser. And we're talking truly mind-boggling density here.
What happens? Does the system just like overheat?
Worse. Gravity just takes over. The whole thing collapses under its own information weight, so to speak, and poof, it becomes a black hole.
Wow, so a black hole is like the universe's ultimate SSD, hitting the theoretical maximum density.
Precisely. Nature's most compact hard drive.
Okay, density limit understood. What about processing speed? Is there a universal speed limit for computation?
There is, yeah. It's related to something called Margolus Levitin theorem. It fundamentally links a system's energy to its maximum computational rate. More energy means potentially faster computation.
But there's a ceiling.
A hard ceiling, yes. Set by fundamental constants of nature, like Planck's constant. You just can't flip bits faster than this limit allows, no matter the system.
Okay, so we have limits on storage density and processing speed. But the really cool part you mentioned is how black holes relate to these.
Right. This is where it gets really interesting. Black holes don't just respect these limits, they seem to saturate them. They push right up against the absolute maximums.
They max them out. How do we know that?
Well, research, particularly by Adam Brown and others, showed something remarkable. They looked at the rate the complexity inside a black hole grows as things fall in, and that rate of complexity increase. It exactly matches the maximum speed allowed by the Margolus-Levitin theorem.
Whoa. So they compute at the universal speed limit.
Effectively, yes. That's why physicists call them fast scramblers. They take incoming information and process it, spreading it across their event horizon incredibly efficiently, faster than anything else we know of.
They hold the record for both density and speed then.
That's the idea, the ultimate information processors in the universe.
Understanding these fundamental limits is actually becoming super relevant for our own technology, especially with AI development. We're constantly trying to scale things up. And if you, listening, are finding yourself wrestling with computational limits, maybe needing help with AI training, automation, or figuring out how AI agents could fit into your business.
Well, this deep dive is sponsored by Embersilk.
Yeah, check them out at embersilk.com. They specialize in AI integration and uncovering where AI can really make a difference, whether it's for business or even just personal projects. Worth a look.
So bringing this back to that AGI ambition we started with, this idea of just building bigger and bigger computers, scaling indefinitely, gravity actually puts a hard stop to that.
You mean if we just keep stacking, say, GPUs together to make a giant supercomputer, eventually?
Eventually, yes.
Wow.
You run into the same problem. The sheer concentration of mass and energy needed for that kind of computation. Well, the calculations suggest if you gather something like 10 to the power of 37 GPUs worth of mass energy.
That's an insane number.
It is. But if you did, its own gravity would cause it to collapse.
Into a black hole.
Into a black hole. So the ultimate supercomputer build is fundamentally limited by gravity. Nature won't let you have unbounded computation in one place.
So physics limits computing power. But you're saying computation can also limit what physics allows us to observe. Yeah. This sounds like it connects to that firewall paradox I've heard about.
Exactly. The firewall paradox is a real puzzle. Does someone falling into a black hole just smoothly cross the event horizon, or do they hit this incredibly high energy wall, a firewall?
And figuring that out, it involves computation.
It involves decoding the information, specifically the Hawking radiation that comes out of the black hole. You'd need to see if the information is scrambled in a way that implies a firewall or not.
Okay, so you just run the calculations.
But there's the catch. This calculation, verifying the state of the outgoing radiation, it falls into a computational complexity class called QSZK.
Which means?
Which means it's incredibly hard. So hard, in fact, that theorists like Harlow and Hayden calculated it would likely take an exponentially long time to perform the necessary quantum computation.
How long did we talk?
Longer than the lifetime of the black hole itself. It evaporates via Hawking radiation before you could ever finish the computation needed to check for the firewall.
So the answer is computationally inaccessible. Nature itself prevents us from easily resolving the paradox through direct calculation.
In a sense, yes. The computational difficulty acts as a sort of barrier to resolving the paradox observationally, at least in that direct way. It's a fascinating intersection of gravity, quantum mechanics, and computer science.
That is wild. Computation literally limiting our ability to probe fundamental physics, which leads to one last, really out there idea. If black holes are nature's ultimate quantum computers,
Then maybe someone or something is using them. Some physicists speculate that extremely advanced Type 3 civilizations might engineer microscopic black holes precisely for computation.
using black holes as tools.
As incredibly powerful quantum computing tools, yes. And this opens up a whole new angle for SETI, the search for extraterrestrial intelligence.
Instead of listening for radio waves.
We could look for the byproducts of their computation, specifically the characteristics of Hawking radiation, high-energy neutrinos and photons that these hypothetical micro-black hole computers would emit, searching for alien computational technosignatures.
Looking for the exhaust fumes of cosmic supercomputers. What a thought. Well, that brings us to the end of this dive into computation at the edge of reality. Mind-bending stuff. If you enjoyed this exploration, please do subscribe to the show wherever you get your podcasts. And hey, if you have a moment, maybe leave us a 5-star review. It genuinely helps other curious minds find us. Thanks so much for tuning in.